Okay, so the title of my dissertation is called Falsification of the Integrated Information Theory of Consciousness. So I'm sure most of you are wondering how this is related to astrophysics. And for my friends and family, you're probably wondering what I've been doing for the past 5 years, but hopefully today I'll kind of explain a little bit of that so that it makes more sense. So I'd like to start with a brief history of biosignatures. So biosignatures are some sort of observation that leads us to believe that life generated the signal. So there's been biosignatures going on basically since astronomy was created. So William Herschel in 1778 suggested that lunar craters were the works of lunarians, and we might as well just call them their towns. So this is not some random guy. William Herschel was a pretty renowned astronomer. And similarly, in 1908, Percival Lowell, so Lowell Observatory up in Flagstaff is named after him, saw the lines on Mars and invoked intelligent Martian engineers as the cause for those lines, or at least a possible explanation. So in more recent times, a really controversial biosignature was the Allen Hills meteor. So in 1996, this meteor was found, and on the meteor, there are these morphological features that look a lot like some sort of life. And so in the original paper, they posited that this was life. And after that, there was a lot of backlash. And now the consensus is that that was not life, and we have yet to find life on Mars. In my PhD career, so just in the past 5 or 6 years, there's been biosignature detections as well. One famous one was in 2015, the alien megastructures star. Basically, there's a star that was dimming with about 20% dips in brightness that were very infrequent. And it was suggested that maybe these were large, a technologically advanced civilization with these big structures designed to capture starlight for energy that were passing in front of the star and causing it to dip. Since then, we basically figured out that it was dust because there's a reddening effect, so that the dip in the brightness changes based on what wavelength you observe. So it turned out that that was dust, but at the time it generated a lot of excitement in the press about potential alien megastructures. And then just recently in 2020, there was an announcement of phosphine on Venus. So in the atmosphere of Venus, phosphine was thought to be detected. There's no abiotic pathways for phosphine on Venus, so it was suggested that potentially life was the cause of this phosphine. Since then, it's come out that that detection was not an actual detection. There's a problem in the data pipeline. So there really wasn't phosphine on Venus. But the point of all this is that in all of these cases, life was proposed as an explanation because there wasn't a known abiotic pathway. So all of these signals, when they were observed, there was no way to explain them with known laws of physics, known laws of chemistry. And so life kind of comes in as this, this alternate explanation. When you've exhausted all other possibilities, life kind of comes in as the next most logical thing. But obviously, the fact that none of these were actual biosignatures kind of leads you to want a more objective way of quantifying whether or not something's a biosignature. So there's actually a way to do this mathematically, and this is the only equation in my presentation, so try not to worry too much about it. But basically, Bayes' theorem gives you a way of quantifying the likelihood of life given some data. And that's a function of things that you know beforehand. So these are called, so on the left-hand side is the probability of life given the data. So this would be a quantitative probability that what you observed was life. On the right-hand side, there's a few important terms. So this p data given no life is the likelihood of a false positive. So basically you have to go through all the known abiotic pathways and put a probability that that abiotic pathway generated the data that you think might be life. And then all throughout this equation, there's this term, which is the probability of life. So this is your prior expectation that life should emerge in a given planetary context. And basically the way this equation works is that you weigh the likelihood of an abiotic pathway as compared to the likelihood of life generating that data. But the problem with this equation is that we really don't know what the probability of life is. So we have no constraint on our prior expectation for the emergence of life. And without that constraint, you basically can't objectively quantify whether or not it's a biosignature. You're always implicitly assuming some prior for what you think the likelihood of life is versus the likelihood of an unknown abiotic pathway. And different people have different priors, which is why biosignatures are so controversial. So what my PhD thesis was trying to do was explain what the intersection is between fundamental physics and life is, so that we might start to constrain the likelihood of life emerging under different planetary contexts. So the working hypothesis that I started with is that information processing is what differentiates living and non-living matter. So if you look at different systems that we think are alive or dead. So on the left, this is just interacting oil droplets. It's kind of like a salad dressing. You have oil and it repels, and you get a dynamical pattern that looks kind of like life. In the middle, you have a colony of ants, which is definitely alive, and you have individual ants and then the colony as a whole. And then on the right, you have a human brain, which is kind of like the epitome of these information processing systems. So the intuition is that oil droplets are not alive, ant colonies are alive, and brains are very alive. And you should be able to quantify that intuition with some measure of information processing. So what I was looking for originally was a quantitative measure of information processing that I could apply to these systems to test this hypothesis that information is what differentiates living and non-living matter. So there's lots of different candidate measures. Information theory is a branch of mathematics that has a lot of different equations, a lot of different possibilities. Just to list some of them, there's transfer entropy, there's active information, and there's integrated information. And the one I eventually settled on was integrated information, not only because it was a measure of information processing, but also it provides a measure of consciousness. So this theory, integrated information theory, already comes tailor-made with this scalar mathematical measure called phi. That's the symbol with the arrow through it. And phi is supposed to be both necessary and sufficient for consciousness. So my original goal was to measure life, but I have this out-of-the-box measure of consciousness. And I think it's not hard to argue that consciousness is probably a sufficient condition for life. So if I can measure consciousness, that system is alive. In philosophy, there's also something known as the life-mind continuity thesis, which states that cognitive processes are an enrichment of the organizational principles and processes definitive of life. So I was kind of implicitly selling this thesis when I organized the scale with the human brain as the most alive. But under this hypothesis, consciousness is, or a measure of consciousness is a measure of life. So basically, consciousness is just like the processes that organize living systems distilled and amplified. But regardless, even if you don't take the strong life-mind continuity thesis, a quantitative measure of consciousness is much further along than any quantitative measure of life. So I thought I should start there, since there's already something in existence, rather than trying to reinvent the wheel myself. And so that's kind of how I got into integrated information theory. So why integrated information theory is so popular, there's several different reasons. First of all, the fact is that it's very popular. So this is a plot showing the past 20 years or so on the x-axis, and this is citations per year on the y-axis. So this includes citations to anything that has integrated information theory in the title or the abstract. And as you can see, integrated information theory is this blue line here. And over the past decade or so, it's basically seen an exponential increase in popularity. And in 2019, it actually surpassed global neuronal workspace as the most popular theory of consciousness in contemporary neuroscience. So if you're a neuroscientist, you've most certainly heard of integrated information theory. And a lot of neuroscience is actually devoted to furthering integrated information theory. So it's a big topic. Basically, the idea that underpins integrated information theory is that consciousness is the amount of information generated by a complex of elements above and beyond the information generated by the parts. So if you're familiar with the definition of what emergence is, this is basically saying that consciousness is an emergent phenomenon. What it means is that if you consider all the individual neurons in isolation, you would never get consciousness. But when they synergize and they sort of synchronize, then you can start to get consciousness as this information that's generated above and beyond what you previously had. So without really telling you what's on the y-axis, the intuition behind the theory is that you have the information generated by the individual parts, and then when you look at what the whole can do, you get this extra boost in something like functionality or information, and that extra something that emerges is consciousness. So that's kind of what underlies the theory. The reason it's so popular, or another reason it's so popular, is because it comes with this out-of-the-box measure called phi that acts on any dynamical system. So for the systems that I was interested in, such as these oil droplets and ants and human brain imaging data, you can basically feed it into a software package called PyPhi. So Pi is for Python, which is a programming language, and phi is this measure of consciousness. And it tells you how conscious something is. So the big phi value, capital Phi, that you get out is the consciousness. So it should be a pretty straightforward problem. I just feed in the data, I calculate the phi value, and then I see if I can get this spectrum from non-living to living systems that recovers my intuition that information processing is kind of what's differentiating living matter from non-living matter. In addition to being easy to use, IIT is supposed to be an experimentally falsifiable theory. So that's a big plus in consciousness studies, where people really struggle to measure consciousness because it's a subjective feeling. But IIT basically has this experimental paradigm where if something is awake, it should be more conscious than when it's asleep. So you can imagine a fruit fly, which is their experimental system. And when you give the fruit fly an anesthetic and it goes to sleep, you should have the prediction that when it was awake, it had a higher phi value, a higher consciousness than when it was asleep. So that's the prediction. If the experimental result validates, or if the experimental result matches that, then it's validated. But if you get the opposite result, that your phi value increased after the anesthetic, then this would falsify the theory. So this is how IIT sort of grounds itself within the experimental paradigm. So that's the basics. My first chapter of the dissertation after the introduction is called On the Non-uniqueness Problem in Integrated Information Theory. What I wanted to do in this chapter was just calculate phi. So the first thing I did, and the first thing I always do when I learn some new mathematical theory, is just try to apply it in a very simple example. So how phi works is it's essentially a measure of the extent to which feedback is present in the dynamics of a system. So on the left, there's a human brain here. And rather than actually work it out for a human brain, I always start with a very simple system. So in this case, this is just a 2-bit digital system. So Q1 and Q2 are basically neurons that take a state 0 or 1. And Q1 acts as an AND gate, and Q2 acts as an OR gate. So rather than work with a big brain when you're trying to understand something, you want to really strip it down to a toy model that's very simple to understand. And so every time you see circuits, you can think that the circuit is basically a minimal representation of the brain to try to understand how things are working in the theory. So for this and or system, the first thing that you have to do is calculate what's called the transition probability matrix. On the left side here are the possible states of the system at a given time step. And on the right side are the same states in the next time step. And so what this tells you is that state 0, 0 at time t goes to state 0, 0 at time t plus 1. Similarly, state 1, 0 at time t goes to state 0, 1 at time t plus 1. So it's basically telling you how the system transitions from state to state at each time step. So if phi is a measure of feedback, what you want to do is imagine a hypothetical cut from this neuron on the left to this neuron on the right. So you imagine cutting this connection, and then you ask, does the transition probability matrix change? So in this case, it certainly does, because now rather than getting the signal from Q1, it gets random noise from Q1. And so if that's the case, then your transition probability matrix changes. And the way the math works is you measure the change in the transition probability matrix. And since there is a change, you find some phi value. So this system is conscious, albeit minimally so. Conversely, if you have a system that does not have feedback between elements, so these are your two neurons, and you can see that these neurons just take input from themselves, Then when you cut the system, this hypothetical cut doesn't change anything about the system because there was no information exchange between components. So you can see at the bottom here, your transition probability matrix is the same on the left and the right. And so when you measure this distance between transition probability matrices, you find phi is 0. So that's kind of the high level overview of how this mathematical measure works. But when you dig into it a little more, it's this really, really complicated process to calculate phi. There's 6 nested optimization steps. So you basically find the minimum of a given step, and then you maximize that, and then you minimize it, and then you maximize it, and you go through that 6 times. And so if you try to do this by hand for even the simplest of systems, it takes forever. And it honestly took me months to just do this one calculation. So the first step to this calculation is that you break the system up into parts, and then you break those parts up into parts. So this is the whole, Q1, Q2 is the whole, and then you have Q1 as a part and Q2 as a part. So each one of these parts is called a mechanism. So a mechanism is just an element of what's called the power set, which is the list of the parts and all the parts of the parts. So step 2 is that you ask how each mechanism constrains the state of the other mechanism. So here you have the past state of the system as a whole, and you ask, what does the current state, so this C in the superscript stands for the current state, the P stands for past. You say, how does the current state of Q1 inform what the past state of Q1, Q2 was? So for that, you look at the transition probability matrix and you select the entries where the current state of Q1 was 0, and you see that for those entries, the past state of Q1, Q2 is either 0, 0, 0, 1, or 1, 0. It can't be 1, 1, because if it was 1, 1, then this would be a 1 rather than a 0. So knowledge of the current state of Q1 constrains what the past state could have been. And so you plot that as a probability distribution. So there's a probability of 1/3 that it was each of these and a probability of 0 that it was this. And this is what's called the cause repertoire. So this is going to be an important piece of vocabulary for the results of this section. So the next step is you ask whether that constraint was integrated. So did Q1 constrain Q1, Q2 as a whole, or just a part of Q1, Q2? And so for that, you say, well, what's the constraint that Q1 current offers on Q1 past? And you basically know that it was a 2/3 probability that it was a 0. When you expand that into the full probability distribution, you compare that to the constraint on Q1, Q2 as a whole, and you measure a distance between these two probability distributions. And this gives you what's called little phi. So little phi is the circle with the slash through it without the big line with the cap. So there's big phi and little phi, and big phi is an optimization over little phi. So little phi is 1/6 in this case. So all of that calculation was just for one mechanism and one current mechanism and one element of the mechanism in the past. So the past is, the elements of the past are called the past purview. You repeat that process for each element of the past purview. And when you do, you find that little phi is 1/6 for both of these elements as well. And these are the corresponding cause repertoires. So you can see this was the cause repertoire we originally calculated, and these are the cause repertoires for these other mechanisms. So the next step is based on the exclusion postulate of IIT, which says a mechanism can contribute to consciousness at most one cause repertoire, and the one that it contributes is the one with the maximum value of integration, little phi. And so if you look at these different cause repertoires, so this is your mechanism, and this postulate says you have to select one of these cause repertoires going forward. The one you select is the one with the maximum value of little phi. But obviously there's a problem here because all of them have the same value of little phi. And so the exclusion postulate says you can only contribute one of these cause repertoires going forward, but you don't know which one to choose, and it's unspecified which one you should choose. This is kind of the first sign of a problem in the theory. Basically, there's degenerate cause repertoires, meaning they all have the same little phi value, but depending which one you select, so let's say, for example, I select this as the cause repertoire with the maximum phi value, little phi value, then after you go through the next steps, you find a value of consciousness, big phi, of 0.09. But if I select this one, I get big 5.25. And if I select this one, I get phi of 0. So you get different phi values for consciousness depending on which cause repertoire you choose. And there's no procedure for breaking this degeneracy and telling you which one to choose. So that was just for this one mechanism. In step 5, you do this same process in the opposite direction. So you say, how does the current state of Q1 constrain the future states of all the mechanism? And you find that, again, you've got these degenerate phi values. And then you repeat this for all mechanisms. You do the same thing for Q2, and then you do the same thing for Q1, Q2. And then you cut the system, like I originally said, and you repeat this whole process. So like I said before, this is an optimization inside of an optimization inside of an optimization. But deep down in that optimization, there's this degeneracy for which core cause you should choose. And depending on which one you choose, you get these different phi values out. And this is a huge problem in the theory that's just not addressed. So you can see that the phi value is changing based on which core cause you choose, and there's no procedure for breaking the degeneracy according to the exclusion axiom. So for the very first system that I ever tried to calculate phi for, I basically found that there's 83 different phi values, and they span the entire range of possibilities. So here is a plot showing the phi values, and this is just rank ordered, meaning it's ordered from most to least. And these are the two different cuts of the system. You can cut the first element to the second and the second to the first. And the one value that's output by the PyPhi code is shown as a white X, but in reality, all of these are equally valid phi values. So there's nothing to suggest that this is somehow more fundamental than the other values. So that got me kind of questioning, well, how does everyone calculate phi if it's got this degeneracy problem? And the answer in short is PyPhi. So PyPhi is used virtually ubiquitously throughout integrated information theory. And that's because this theory is so dense to get through that I don't think anyone actually goes through it unless you're a grad student and you have 6 months of your life to try to figure out how it works. But basically in PyPhi, you can see the relevant part of the code for breaking the degeneracy is this line here. It says if phi is less than phi MIP. So in this case, it doesn't say what to do if phi is equal. So this is the little phi. If little phi values are equal, there should be some criteria for breaking degeneracy. But as you can see, the little phi, it just selects the one that's less than, which means if it's equal the next time, it just throws it away without considering the fact that they were equivalent. So what I did is I rewrote PyPhi. I called it PyPhi spectrum. And rather than just throwing away these degenerate core causes, I kept all of them so that you could calculate all the different phi values rather than selecting one of them arbitrarily. And so as you can see, so this is a survey of publications where they published a phi value using PyPhi. There's 10 different publications. You can see Sara and I are on here. I was aware of this problem at the time, but I wasn't really sure of how to go forward. But basically all these X's are in individual phi values. This is a publication talking about consciousness and saying that this system has this value of consciousness. And then a narrative is created around that value. In the discussion section, they talk about it's got this consciousness because of X, Y, Z, and this makes sense because of whatever. If you reanalyze this corpus with this PyPhi spectrum code that we wrote, you find that basically none of these values are unique. So all of these different dots are the equally valid phi values that you get out for these systems. So here you can see the Andor system with the 83 different phi values. And then you can see all these other papers that published phi values. They were really just selecting one arbitrarily, and it was an idiosyncratic aspect of the PyPhi code, which one gets selected. And so to summarize this first chapter, virtually all the published phi values were selected arbitrarily. Crucially, a lot of these systems include both phi equals 0 and phi greater than 0. So phi equals 0 means the system is unconscious. Phi greater than 0 means the system is conscious. So you can see for this Marshall et al. System, phi equals 0 is just as valid as phi equals 1. So that completely changes the conclusion of the paper, which is basically saying this system is conscious, but it's just as likely that it's not conscious, which changes the results. So the point of all this is that IIT is actually not well defined mathematically. These degeneracies need to be resolved. And if they're not, it's not a measure of consciousness that you can actually apply in a setting and trust the outcome. So temporally, so this degeneracy problem, I knew about it for a long time, but I didn't know exactly what to do about it. So rather than publishing on that, I actually published this paper first, which is called Integrated Information Theory and Isomorphic Feed-Forward Philosophical Zombies, because I was trying to dig into the foundations of the theory and understand how any of it's justified, and just really try to figure out if there's a way around this degeneracy problem. And so IIT is what's called the phenomenology first theory. So there's three axioms of the theory: information, exclusion, and integration. Information says that conscious experience generates information by being one of many possibilities. So it basically says when you have a conscious experience, the fact that it's one of a set of possibilities is informative. That's translates well to a mathematical notion of information from information theory. So exclusion is the second axiom, and it basically says that simultaneous experience is not allowed. So this is what keeps experience localized and bounded. So the fact that you and I have different subjective experience is a consequence of exclusion because there's no overlap between experience. And the last axiom is the integration axiom, which says consciousness is experienced as a unified whole. So the way that they present this often is that when you look at a blue triangle, you don't experience blue and a triangle as separate, you experience it as unified. That never made much sense to me, but what does make sense is that your left and right visual field is integrated into a single whole. So it doesn't make sense to consider your left and right visual field as separate experiences because that experience gets integrated downstream into a single unified whole. So those are the phenomenological axioms of the theory, but in order to be a scientific theory, and especially to have this mathematical measure, these axioms about phenomenal experience, which is conscious experience, have to be translated into something about physical processes that embody or instantiate these axioms. So the first postulate is this stuff about information corresponds to Shannon information, which is a mathematical theory of information. So you don't actually need to know much about this postulate other than it provides a way to put math to a lot of these terms. The second postulate you actually already saw. So the integration or the exclusion postulate says a mechanism can contribute one cause repertoire, and that's the one with the maximum little phi value. So like I said before, this is an extremely problematic postulate. And the third postulate is that feedback is a necessary condition for consciousness. So basically on the left, you have what conscious experience is like, and on the right, you have the physical process that translates that phenomenological axiom into something we can measure. And that translation step is what's known as the hard problem in philosophy. And the hard problem is famous for being very, very difficult to solve. So whenever you assume this leap from phenomenological axiom to physical postulate, it's a really big deal because a lot of philosophers have said that it's impossible to close that gap. It's this metaphysical divide that you can never solve. But obviously some people and proponents of IIT believe that you can solve this problem. And the way that they solve it is by assuming that feedback is what gives this experience of a unified whole. So you can't have this holistic experience without feedback between neurons or between elements in your system. So my question in this chapter is really, how does IIT justify this proposed solution to the hard problem? So this is a big claim that physical feedback is what generates conscious experience. And I was basically just trying to understand the rationale behind that claim. And the justification is primarily one of experimental tests. So like any science, IIT leads to predictions, for instance, that the loss and recovery of consciousness should be associated with the loss and recovery of integrated information. So IIT is going to try to justify this integration postulate with an experimental test. The experimental test that they go to is the fruit fly example that I was talking about earlier, where they have fruit flies that are awake and they anesthetize them, and then they measure their phi values. So in the experimental paradigm, you validate if the phi value is greater when it's awake than when it's asleep, and it's falsified if it's if phi value is less than when it's awake than when it's asleep. So this experiment was actually done. You can see the citations on the bottom here. And what they found is that when the fruit fly is awake, it has a high phi value. So this says little phi on the y-axis or on the z-axis, but this is the consciousness that they're measuring. And you can see that it's non-zero. So the fruit fly, when it's conscious, has these high phi values. And when it's anesthetized, you can see that the phi value decreases. So in this experiment, this was taken as confirmation of the prediction that phi of a waking fruit fly is greater than phi of a sleeping fruit fly, and therefore phi decreases when you lack consciousness. So that was validation for phi. The problem was that I came across a different theorem, or I came across a theorem in a different area of research called the Krohn-Rhodes theorem, which technically states any deterministic finite state automaton is a homomorphic image of a cascade automaton, blah, blah, blah. What this translates to is that any transition probability matrix is a functionally indistinguishable representation of a strictly feed-forward system comprised solely of simple elements. So what this means from an engineering perspective is that you can get rid of feedback without changing the functionality of the system. So if you translate the Krohn-Rhodes theorem into the language of IIT, what it basically says is that every system with phi greater than 0 has a functionally indistinguishable counterpart with phi equals to 0. And the way that you get this counterpart with phi equals to 0 is by getting rid of the feedback. So the integration postulate says feedback's necessary for consciousness. The Krohn-Rhodes theorem says you can always get rid of feedback with no effects on functionality. And so if this is the case, then the system that results after you get rid of feedback is what's called a philosophical zombie, which means it looks, for all intents and purposes, like a conscious system. It behaves the exact same way, but it's supposed to lack subjective experience. So if we return to the experimental paradigm, we had this case where the fruit fly was awake and it has high phi, but under Krohn-Rhodes decomposition, you should get a fruit fly that looks the exact same. It's still awake. It should respond to all the inputs in the same way, but you get phi equals 0 because you've, in theory, rewired the brain to get rid of all feedback. So if this is the case, then when you compare the phi value of the fruit fly when it's awake to the phi value of the anesthetized fruit fly, which is minimally conscious, you should find that the fruit fly that's awake is less than the fruit fly that's asleep. So this would actually be falsification in the experimental paradigm. So I'll just take a break for a second. Okay, let me make sure everyone's still with me. Okay, yeah, so I think everyone's still here, but yeah, the idea is that the Krohn-Rhodes theorem proves that no matter what the behavior of a system is, you can fix the behavior with phi equals 0. So that should mean that this fruit fly that's awake, you can make a philosophical zombie version that's still awake, but it has phi equals 0, which in their experimental paradigm would imply falsification. So under Krohn-Rhodes decomposition, IIT is already falsified without the need to do any experiments. So this is kind of confusing because right when I was sort of proving these results to myself, IIT got a huge grant, so $20 million plus to test phi in experimental settings on humans. So to test the scheme, there's going to be all sorts of experiments. So a bunch of different labs got $5 million each, and they're basically going to measure phi in humans. But the Krohn-Rhodes theorem guarantees that no matter what the results from the experiment are, the opposite result is possible. So no matter what the phi value is in the human brain, it's possible to rewire the brain without any outward effect and have phi equals 0. So this was kind of a confusing time, but at that point, I just summarized the results as the Krohn-Rhodes theorem guarantees that feedback is decoupled from function. So you can always fix function and get rid of feedback. IIT relies on function to test predictions. So every system with phi greater than 0 has a functionally indistinguishable counterpart with phi equals 0. And therefore IIT is falsified a priori. So the basic idea is that in IIT you decouple feedback from function. And if you try to use function to make experimental predictions, then you'll always be able to vary the phi value with fixed function. Okay, so the next chapter was called Formalizing Falsification for Theories of Consciousness Across Computational Hierarchies. The way that this project started was basically IIT admits philosophical zombies openly. So this is very confusing, but according to IIT, feed-forward emulators are not conscious. So what this means is that in the experimental paradigm, you have this fruit fly that's awake and it's conscious. And then if you perform a Cronrhodes decomposition so that it's a feed-forward fruit fly, IIT says that it's unconscious. And the reason that it's unconscious is because of the integration postulate. So after Cronrhodes decomposition, it lacks feedback. And so because the integration postulate says feedback's necessary for consciousness, this system has to be unconscious. But this is extremely problematic because the whole point of this experimental paradigm was to test the integration axiom, or to test the integration postulate. So the fact that the integration postulate's used as justification is this circular loop that you can't break out of. So this was just very, very confusing to me. So we were trying to test the integration postulate, but every time the experimental results didn't match, so if you found this, then the integration postulate was used to defend the theory. So this was kind of a confusing point in my PhD career because I didn't really know what to do or say about this problem, but I felt like it was a problem. And the answer was to turn to philosophy of science. So whenever you're really, really confused, philosophy can help alleviate that confusion or make you more confused. In this case, it ended up helping. This is a really good book. I actually got this book from Cole. It's called Theory and Reality by Peter Godfrey Smith, and it's an introduction to the philosophy of science. And a big component of philosophy of science is what's known as the demarcation problem, which is the difference between science and non-science or pseudoscience. And the key feature of a scientific explanation is to work out what difference it makes to things we can observe if the explanation were to be true. So the difference between something like physics and Freudian analysis is that in Freudian analysis, it makes no difference to anything we can observe if it's true. So every observation can be described within this framework. And the same is true for stuff like Marxism and astrology. So basically, if something's supposed to be scientific rather than pseudoscientific, you have to work out some sort of observable. So with that in mind, I tried to actually perform a Cronrhodes decomposition. So the thing about mathematical theories is that they prove that these things exist without actually showing you how to do it. So in the previous paper, I had basically argued that it's possible to unfold the feedback in a system so that you get feed-forward systems. And in this paper, I actually did it. So on the right, you can see that this is a simple electronic toll booth. So the reason I chose a toll booth was because in automata theory, in like the late 1960s, toll booths were kind of this prototypical system, and that's where I was learning everything from. So I stuck with a toll booth. And here you can see I designed a circuit for this toll booth that operates it correctly. And according to IIT, this is a conscious toll booth. So the fact that this circuit has feedback, it's like a mini brain, and you basically find phi is greater than 0. So then what I did was I actually performed a Cronrhodes decomposition, and I did it isomorphically, which I'll explain in a bit. But basically, I made a new circuit, and this circuit is feedback free. So it's kind of hard to tell here, but these three squares are the neurons or the bits in the system, and it's unidirectional information flow. So this is an unconscious toll booth according to IIT. So the fact that I did it isomorphically was really important to the set of arguments, because what the isomorphism does is it guarantees the same input-output behavior for these two circuits. It's the same functional topology, which means that even internally, the states that the system is flipping through are in one-to-one correspondence. So there's a one-to-one map between internal states. And there's the same memory constraints. So up until this point, no one had ever demonstrated that you can get this feed-forward philosophical zombie under the same resource constraints. So here, each system operates on a 3-bit architecture, and you can actually easily build these systems at home. It would take, an afternoon to wire this up, but basically the point is that they're both 3-bit systems. So you can't say that the conscious system is more or less efficient than the unconscious system. And at an abstract level, these are actually the exact same computation. So the way that I built these circuits was starting with a computational description of the system and then projecting down into 2 different instantiations. So at an abstract level, these are actually the same mathematical structure. And what this all proved is that the presence or absence of feedback makes no difference to things we can observe. So all of these are things that would be additional consequences of feedback. And basically you can show that there's no additional consequence to the presence or absence of feedback. It's basically an arbitrary property of the system. Since feedback is necessary for consciousness, this translates to the statement that the presence or absence of consciousness in IIT makes no difference to things we can observe, which in turn implies that IIT is a metaphysical theory. So in summary, IIT assumes that the absence of feedbacks justifies the claim that philosophical zombies are unconscious, but the presence or absence of feedback has no additional consequences. Therefore, the integration postulate can't be tested. And so IIT is a metaphysical rather than a scientific theory. So if you choose to believe in the phi values, there's never going to be a way to test that step from the phenomenological axiom of the theory to the physical postulates. So that brings me to the conclusion. So the conclusion is titled, what theories of consciousness teach us about defining life? So both life and consciousness are what's called a pre-theoretical science. And that means that we're trying to study the topic of interest in absence of an existing theory. So it's a very different type of science than things that have existing theories that you can use to as a tool set to find new results or building on the theory. But a really good example of what the difference between a theoretical and a pre-theoretical science is trying to define water prior to molecular theory. So before molecular theory, water was defined as something like a colorless liquid that boils at 100 degrees. So in this definition of water, you see water is what we're trying to define. And you basically equate this with a list of salient features that we ascribe to this system or this word. But after molecular theory, you have the definition that water is H2O, and H2O provides a causal account for why water has the salient features that we attribute to it. So basically, when you have a scientific theory, you now get an explanation for these salient features, whereas without a scientific theory, all you're doing is equating a word with a list of attributes. So if we apply that same sort of argument to consciousness, so IIT was trying to make this transition from, pre-theoretical to theoretical, and life is going to try to make that same transition. But a definition of consciousness prior to IIT is something like consciousness is an integrated, informative, exclusive experience. This is the list of salient features, whereas after IIT, the definition changes to something like consciousness is phi. And so what phi does is explain the salient features of consciousness. And the way it does this is by connecting the phenomenological axioms, which are the salient features, to a causal explanation, which are the physical postulates. So this is the hard problem. The hard problem was actually making the jump from pre-theoretical to theoretical science. And IIT did that. It made this jump. So it's epistemologically grounded, but the problem was that the way it did that didn't have any consequences in terms of testable hypotheses. So the demarcation problem, again, is that if this solution is true, there has to be additional observables. So for example, with water as H2O, if water is H2O, then, and then you have a whole suite of experimental predictions that result that allow you to test this connection. So for example, you should be able to produce hydrogen through photodissociation if you have this molecular theory of water. if consciousness is phi, then needs to have some set of predictions. So unfortunately, there's no predictions that come about if consciousness is phi, because IIT decouples phi from function. It basically says that you can have consciousness without any additional consequences. So even though it made this leap from pre-theoretical to theoretical, there was no testable consequences, which basically just underlies the fact that scientific explanations have to have observable consequences. So if we now turn to definitions of life, so this is the definition of life that's accepted by NASA, which is that life is a self-sustaining chemical system capable of Darwinian evolution. So here you have life, and then you have a list of salient features that we attribute to life. So a definition of life after a working theory of life might be something like life is a certain type of complexity, or this could be anything really, but basically what's in red here is supposed to explain the salient features of life. And where we're getting to now in origins of life science is basically where theories of consciousness were 20 years ago, which is try to make that transition from pre-theoretical to theoretical explanations. So for example, pathway complexity is proposed as a basically a measure of life. So this quote is from Marshall 2017. It says, "We propose pathway complexity as the natural measure of complexity for the production of artifacts. In this context, we argue that there is a critical value of pathway complexity above which all artifacts must be biologically derived." So in this example, basically they're saying that pathway complexity is a measure. If you have a pathway complexity over a certain threshold, then that is a sufficient condition for life. So the key question that must be asked is, what difference does this make to things we can observe if it's true? So if all we're doing is going around and labeling different pathway complexities, so if you say, computer has high pathway complexity, a rock has low pathway complexity. If all it is a labeling scheme, then that's not a scientific theory. So what needs to happen is basically you need to have some sort of prediction about what would falsify the theory. So for example, if you find high pathway complexity in the absence of life, does that falsify the theory? So with IIT, this same sort of principle held. So basically the idea was that if you find low phi in a conscious system, then the theory should be falsified. But somewhere along the line in the development of IIT, the original predictions lost the ability to be falsified. So we found systems with low phi that were conscious. These should be the philosophical zombie systems. But at some point, IIT became its own justification scheme. So what should be avoided for theories like pathway complexity going forward is that you can't use the value of pathway complexity to dictate the interpretation of whether or not the system's alive. So you have to make predictions, and you have to test those predictions independently. You can't use your theory as a lens to see the world without any sort of outside check. So there's nothing wrong with pathway complexity at this point. The message is just to be very careful that you have falsifiable sense, and that pathway complexity doesn't become its own justification scheme, which is basically what happened to IIT. So on a related note, with regards to biosignatures, there's this important question of when life is a viable explanation. So as I mentioned in the introduction, the detection of life should not be as simple as ruling out known abiotic pathways, because for any unexplained phenomenon, the probability of an abiotic pathway may be less, the probability of an unknown abiotic pathway may be less likely than the probability of life. So in both the Herschel example with the moon and the Lowell example with Mars, there was no known geophysical process at the time that could explain these results, and so they invoked life as an explanation. But in both cases, obviously it was found out later that there is an abiotic pathway that explains these, and that was the actual solution. So I think the key is, again, you have to work out what additional consequences occur if that explanation is true. So if these really are lunar cities, you're not done at that point. You have to then predict what should happen if they were lunar cities versus if they weren't. And without that extra step, the theory is ultimately metaphysical. So the next thing for biosignatures, or at least one promising area, is the James Webb Space Telescope, which is basically going to characterize atmospheres on exoplanets. And if life is proposed as a scientific explanation, it must have additional consequences. So with the James Webb Space Telescope, if we find oxygen on an exoplanet, we can say that it's life, but that doesn't become a scientific explanation unless we work out an additional consequence that would be true if it were life. So that's kind of the message going forward. And that's the end of my presentation. So yeah, I'd just like to take a minute to acknowledge everyone. Obviously, Sara has funded my past 5 years, and also given me the freedom to think about all this. My parents, my friends and family, my in-laws. Yeah, so I think with that, I'll end. Thank you.
Thanks, Jake. That was great. So I'm sure we'll have questions from our audience, and we already have a question from Paul in the chat, which I can read just to get us started, which is with respect to the Krohn-Rhodes theorem. It refers to a finite state automaton. Are the states discrete/countable? Real conscious beings, e.g. me, are open systems and presumably analog rather than digital. Is this a loophole for IIT?
Yeah, I think that's an argument that definitely applies to IIT. So every system in IIT is automatically considered as discrete. So I start with any system for which there's a valid phi value for, which is already a discrete system. So any finite state machine is, so a transition probability matrix is a finite state machine with a single input, and I'm already in the assumption that it's discrete, which is the assumption that IIT adopts. So if that's a problem, then it's a problem for IIT as well.
Right, okay, thank you.
Yep.
Other questions? Steve Ruff has your hand raised.
Yeah, thanks. So I'm curious about the idea of, how did you call it? Additional consequences or predictable consequences? Is it PC? Is that what you said?
For pathway complexity, yeah.
Yeah. So I think unstated in that is that there has to be some way of observing or recognizing those consequences, right? I mean, you can't just say that there needs to be that, but there also needs to be a way, or they have to be observable, yes?
Right, yeah, observable consequences.
Okay, so for example, with your exoplanet example of oxygen, what would be a predictable consequence of that you could then observe?
For the exoplanet example? Yeah, I think that's a really hard question, but I think that might be something that's limiting for the field of exoplanets. But I guess an ideal example would be something like a seasonal variation, even though I don't think that's possible. But if you could say, so let's say you predict oxygen and then you say, well, if it's, photosynthetic life, then you should have this seasonal modulation. So something like that, but I don't think that it's going to be easy to do that. That said, the only reason you need these additional consequences is to try to give a scientific explanation. So you can posit that it's life if it's oxygen, or if it's a redox disequilibrium. You can posit that it's life, but you can't prove that it's life. And so I don't think there's anything wrong with saying life is a possible explanation for this. And then if you can't find any additional consequences, that's fine, but then you just can't make that final transition to saying that this is for sure the explanation.
Got it, thanks.
Yeah, thanks for the question.
I have one. Good talk, Jake. So in regards to IIT's phenomenological axioms, do you take issue with them just at this base theoretical level? Or do you have any comments on them?
So I take them at face value. There's a lot of philosophy out there that takes issue with it. So basically every phenomenological axiom has at least one paper that says that it's wrong. And I don't really get into any of that because I think that's mostly for philosophers. But yeah, you can argue that each of the axioms are wrong, and people have argued that. And you can also argue that the translation from axiom to postulate is not unique, which I think is a really strong argument. So you can say, even if you accept these three axioms, the mathematical measure that they get is not the only one. There's many different mathematical measures that you could get that are entirely different that still fit with these axioms. I also don't go down that road. So I just go down, take the axioms at face value, take the definition of phi at face value. But yeah, at each step you could argue it.
Cool.
So I think Cole had his hand raised, and then we could go to Brian's question in the chat after that.
Jake, great talk. I just wanted to maybe follow up on this question about other observable consequences. And so you leaned really hard on, I think, a pretty solid use of the demarcation, or solid solution of the demarcation problem. But people have thought about this in terms of, like, you know, science is an endeavor that's never really done, right? And so you'll be biased towards theories where you can already measure things if you stick to that sort of strictly. So you need some sort of flexibility in, like, actually, I might not be able to measure this yet, but in principle it could be measured, or maybe the first measurement that I made was not very good, but, like, actually I need to go build a better telescope or a better microscope or a better instrument to measure it. So do you see anywhere in what you've looked at with IIT, I mean, you've dug down pretty hard, but do you think that there's anything where it's like, actually, maybe there's ambiguity and this isn't exactly falsified, but this auxiliary theory or this thing that you have to bolt on to IIT has been falsified?
Yeah, absolutely. So the reason I simplified this whole thing is because I think that aspect of the demarcation problem is the easiest to understand and the easiest to present. If you dig into the nuts and bolts of, you know, the way science works and what falsifiability is, yeah, you find that it's not clear at all. And with respect to IIT, it's not so much that there's not additional consequences. There's a lot of other evidence that it's been an unscientific handling of core ideas since the get-go. So IIT's been iterating on ad hoc solutions for a long, long time now. And, you know, research programs are supposed to be sort of adapting and changing. So you can say that science is good science if you have a research program that's constantly evolving. And so in that lens, a lot of people argue that IIT is good because it's always evolving. You know, falsification isn't a clear concept as long as you're always changing. But the way that it's changing is really toxic because it hides the problem until it's revealed. And then when it's revealed, you get an ad hoc Band-Aid on the problem. And it's really just this unhealthy progression that's never actually had any real experimental observations to support it. So in any paradigm, you want your canonical examples that sort of ground the paradigm and say, like, these are the things that really are the pillars of the paradigm. And IIT, like, never really had any of those pillars. And then it's got all these ad hoc solutions that really make the research program iterating just seem unhealthy rather than healthy. But yeah, falsification isn't as clear as just, you know, you have a testable hypothesis. Is it true or is it false? Although that's how IIT itself sort of presented itself with this experimental paradigm.
Thanks.
Great, we can go to Brian's question. Brian, I don't know if you want to ask your question live or you want me to read it. I can read it if you don't want to unmute. It's okay. Okay, I'll read it. Nice talk. It seems to me there would be an additional, maybe perturbative experiment that could distinguish the conscious and unconscious toll booths, or at least you could follow the wires. Is there an argument against this?
Yeah, that's a great point. So these isomorphic systems are not really isomorphic if you were to intervene on them. So the fact that you have different circuit structures means that if you go in there and you cut a wire, the response to that cut is going to be different for those two systems. So you can resolve that they're different. And if you have a theory of consciousness that has something to do with responses to perturbations, so if you say conscious systems are robust to perturbation, and that's sort of the core idea of your theory, then under this isomorphic Krohn-Rhodes decomposition, you'll have different responses to the perturbation, and you could argue one is more or less robust. But the problem is that none of that is in IIT. So I strictly limit my scope to what IIT is talking about. And within the confines of that limited scope, there's nothing about perturbations or robustness. It's only based on, how does it process or how does it transition between states? And you can map those to functional states and show that, these are the same functional topologies. So yeah, I think a better theory of consciousness would take into account some sort of dynamical response. And in that case, integration might be important. But yeah, at this point, IIT doesn't say anything about that.
Brian says agreed, thanks. Cool. The next question, so we have a couple more questions in the chat. I think we'll go through those and then we'll let everybody go and get to the committee discussion. So this one comes from Angie, who says, great job, Jake. I was constantly trying to understand IIT from a physiological perspective. IIT also seems limited to how physiologists are measuring consciousness. Can you comment on if studies using IIT use a mix of methods?
So I think IIT is kind of in like the baby stages of actually being measured in labs. So the way that the computation works is it's so computationally involved that you can't actually measure IIT for systems with more than something like 10 neurons. So ideally, you'd have you'd have fMRI data and you'd translate that into a TPM and you'd measure that. And that would be the method that you use to actually measure IIT. But in practice, the computation takes so much time to do that no one actually measures IIT in practice. And the experimental paradigm with the fruit flies is actually using an approximation to IIT, which is itself extremely problematic. So the approximation, you can basically prove, does not recover what the postulates of the theory say. But yeah, the point is that there is no real experimental measuring of this in labs. But the theoretical methodology would be to get fMRI data, turn that into a transition probability matrix, and then calculate phi for that system. But I think anyone that works with fMRI data also knows that fMRI data in itself is not that reliable. So yeah, there's kind of problems throughout the whole process.
Excellent. And that's actually a good segue into Yambo's comment, which I think is more of a comment and a question, but you probably will definitely have things to say about the comment. So I'll read it. I guess another problem / topic of IIT is how they define the measurements. If people want to do measurements on or experiments on the brain, they need to measure part of the brain, which is kind of a coarse graining. But how can we validate the relationship between measurements on coarse grain observations to measurements on micro observations? This topic hasn't been discussed on IIT, but it maybe is a problem. Do you have comments on that, Jake? I'm sure you do.
Yeah. So I don't really have the answer to this question. They try to address this in IIT. So basically the problem is that depending on the scale you look at the system, you're going to get a different transition probability matrix out, and you're going to get different phi values for the same system depending on the resolution. In IIT, they tried to address this. There's a paper by Eric Hole about basically coarse graining and then looking at the phi values. And their solution is that you coarse grain over all possible resolutions and you select the one with the highest phi. So it's just a 7th optimization step where now not only do you look at all the different cuts of all the different systems, now you apply all the different coarse grainings on top of it. And then once again, you apply the exclusion postulate to say the highest phi value coarse graining is the true one. But yeah, I think there's better ways to go with this problem of coarse graining. And I think you'd want something that's more self-consistent than what they do. But yeah, I don't actually have an answer to the coarse graining problem. And I know it's something that Yambo has thought about quite a bit. So yeah, I don't really have anything to contribute in that regard, but yeah, IIT is aware of it and they solve it with this additional optimization.
Great, thanks. All really great questions. So thanks everybody for that. So at this point, I think we're going to excuse our audience. And so the committee can stay on.